All right. Now I've got to stop some local echo by turning off my audio here. Great. Okay. So is that coming through okay?
Quick question, Tridge. So this is the time slot you'd swapped with Tom for?
That's right, yes, because Tom didn't have his slides ready, so he asked if he could swap. And so we're running a little bit ahead of schedule, which is great, because some of the talks might go a bit long, and so it gives us plenty of time for questions. So Tom is going to be tomorrow morning.
Yeah, tomorrow morning, exactly. Thank you.
That's right, Tom will be tomorrow morning, and I'm giving my systems update starting up in just a minute. All right. All ready, Randy? All the recording and things?
Yep, I think I'm already recording. Yep.
All right. And if anyone wants to follow along my slides, there's a link to my slides in the schedule. And so you can click on that and follow along and look ahead and work out which of the boring bits you're going to go away and have toilet breaks and coffee in. So I'm going to share my screen and then start the presentation. Now, just confirm that everyone can see that okay?
Yep, looking
Confirmed.
good.
Yep.
Okay, great. All right. Well, thank you for joining in. So this is a systems update. This is something I've done for the last few years, give a sort of update of the overview of what's happening in the project as far as low-level drivers, the RTOS, the HALs, that sort of layer. And so that's what I generally call the systems level of ArduPilot, as opposed to the sort of higher level flight control and state estimation and other areas. So to kick it off, I thought I'd give a bit of a summary of how things have been going over the last year. It's been a very big year in terms of development. There's been a lot going on. We've had a total of over 5,000 patches have gone into ArduPilot, representing over 3,000 PRs going through in the last year, which is really quite incredible if you think about it. That's an awful lot of code, an awful lot of code review, a lot of development. And a total of 173 people have contributed to just the main ArduPilot repository. That doesn't include all the contributions to the documentation and Mavlink, PyMavlink, you know, all Mission Planner, and many other repositories that make up the overall ArduPilot ecosystem. Also, just in terms of code change, the total number of lines of code that have changed in some way in the last year is 280,000 lines of code. And that's just in the main ArduPilot repository, only counting the C++ and header files. And we've only got 500,000 lines in the repository. So that means that more than half of the lines of code in ArduPilot have had a change in some form in the last year. Probably about half of those is spelling fixes from Pete Hall's patches, I would guess. Sorry, Pete. But so a very large amount of code changes in the last year. And so it's been huge contributions by the team, and really greatly appreciate everyone pitching in. Firmware size has become a bit of an issue over the last year, and I've put there the firmware size for the FMUv3 firmware over the last 4 years at about the time of the developer conference. And you can see back in 2018, it was about 940 odd K, 938. Leapt up with a huge number of features. We had a very big year, 2018, 2019. We leapt up to 1.3 megabytes. So also we changed the default optimization to be 02, I believe, which increased that on the 2 meg boards. A bit smaller for 2020, and then another huge leap in the last year, another 200K. So we are actually, if you extrapolate out a little bit, we're going to start running low on space on the 2 meg boards fairly soon, particularly on the F7 2 meg boards, which use flash for storage, because and the H7 as well. So for example, an H7 2 meg board uses 3 sectors, 1 for the bootloader, 1 and 2 for the flash storage, which means, you know, 3 times 128 That's a lot of flash being used with taken out of your 2 meg that you can't use for code and data. And so we've got to start thinking very seriously about flash space. It's even more critical on the 1 meg boards. And so just on the right here, I've put a little table as of this morning, the 4 boards that have the least flash space free. And these numbers here are in bytes. So that's the number of free bytes we have on those 4 boards. And this is one, the Omnibus F4 Pro is one that Henry Wurzburg flies a lot. And he noticed, for example, that some current pull requests, if he applies them to master, then his favorite board, the Omnibus F4 Pro, doesn't build anymore. This is with plain. The copter build still has a bit free, about 20K free on those, but the plain build is very, very close. So what that basically means is that we are getting a bit of a critical issue with some boards as far as flash space. And so we've been talking for a while now about a custom firmware server where we have a custom.ardupilot.org that operates somewhat like our terrain firmware server, terrain download server, terrain.ardupilot.org. If you've never seen that, then pop in terrain.ardupilot.org into your favorite web browser and you'll find it's a very useful tool. We're hoping that we'll be able to get a custom firmware server as part of a GSOC project over the coming months. And we've got a promising candidate student who's applied for that. So I'm hoping that that will be successful. And with the custom firmware server, it'll allow users, for example, on the Omnibus F4 Pro, they could turn off a whole bunch of features to be able to, turn on just the features they need. In order to do that, it does mean we're going to have a lot of restructuring of the code over the coming months to take full advantage of that capability. For example, I would like to make the quad plane capability in ArduPilot optional, which will cut out all of the VTOL support, all of the copter support, AP motors, etc. And that would be probably 150 or 200K maybe worth of firmware space, around that order, maybe 100K. I haven't actually measured it because I haven't got that optional yet. And that would make it possible to, if you're flying on a pure fixed wing platform, you don't have VTOL, you'd be able to deselect that and save a lot of flash space and get a custom build. But I suspect by this time next year that a fairly significant part of our community is going to be flying custom firmware builds with just the features that they want. And so it's going to become more and more important as we get these new features, because a lot of our recent features have been very flash heavy. I forgot to say at the beginning that I'm very happy for people to ask questions during the talk. So feel free to just unmute yourself and pop up a question if you'd like to. And I don't have the chat open, so I won't notice it in the chat. So, but if you don't have a microphone, then pop it in the chat and somebody else can relay the question if they've got a microphone. All right, so that's basically what's been happening as far as development summary. So very rapid development, but there's a consequence of that rapid development that we are consuming our remaining flash space fairly rapidly. We do have a bit up our sleeves on the 2 meg boards because they're currently built with optimization 02. Most of them are. We can switch that across to space optimization if need be with a little bit of a performance penalty, and that would save us a bit of flash space. So we do have a few options to delay the problem of running out of flash in the 2 meg boards. We don't have as much luxury on the 1 meg boards because we're already doing that on our 1 meg boards. All right, next major thing that's happened just recently is the shift to ChibiOS 20.3. We were on a 2018 version of ChibiOS, and we've been on that for quite some time. And we recently updated it to the 20.3 version. It was really quite an uneventful change. And I'd like to say greatly appreciate the assistance from Andy Piper and Sid in that shift to the 20.3 ChibiOS. They both contributed a lot, especially Andy in that work. It was actually mostly fairly minor bug fixes, made it quite an easy update. It was easier than the previous RTOS update. There was a few little tweaks we needed to make. But that got us a new release. The reason for the update, the motivation was twofold. One was supporting some new microcontrollers, in particular the new G4, STM32 G4 microcontrollers. And the interest on that was the G4 is a low-cost small microcontroller that supports FD-CAN. And over the coming months, I think that there's going to be quite a bit of emphasis on supporting higher speed CAN bus. And this is mostly because high speed CAN bus just gives us more bandwidth. And we are already finding that if you have a lot of CAN peripherals enabled, for example, CAN ESCs and CAN servos, if you enable a lot of those at the same time, as well as GPSs and other devices, rangefinders, etc., we're pushing the limits of the 1 megabit CAN. In practice, with 1 megabit CAN, you get about half a megabit of practical bandwidth available with all the overheads of UAV CAN and the framing, etc. And we're basically, utilizing most of that on a machine that's set up, for example, a quad plane that's set up to you for all of its VTOL motors to be CAN ESCs and with some extra CAN servos, etc. It's running quite close. So I think we're going to be pushing things on FD-CAN, and so having a microcontroller for a low-cost AP peripheral based on the G4 microcontroller is going to be really good. And there's already 2 companies that I'm aware of that are developing AP based peripherals based around the G4 microcontroller based on this work. It also adds support for QSPI,
yeah.
And so
Tridge, I have a question.
There? Yep.
Yeah, does that mean we're going to move to the UAV CAN 1.0 spec?
So I addressed that a little bit later in my talk, but the basic answer is that we'll probably support UAV CAN V1, but Sid and I are also considering the possibility of supporting a variant of V0 that can handle higher data rates. And that's quite attractive for various reasons, but I'll discuss that in a bit more detail later in the talk.
Okay.
So also adds QSPI support. So QSPI support allows us to have external flash. So flash that's not incorporated directly into the microcontroller, and instead have the code and data on an external flash chip. And that's something that Andy Piper's been working towards on a racing board out of the UK that supports that. But I think more and more flight controllers are going to move to having a few megabytes of QSPI flash. And Andy's got a draft pull request up for that on this one board. And it's going to be quite interesting because it means that we'll be able to start expanding flash size without having to move to a new generation of microcontrollers with 2 mega flash, because basically ST doesn't really have microcontrollers in the class that we use that have more than 2 mega flash. So having the ability for some new flight controllers in the future to augment their flash space with a QSPI flash part is going to be very valuable to be able to cram all the features we want into the flight controllers. So really interesting work being done by Andy, and I'm be very interested to see when that's fully working. And so that was a strong motivation to move to 20.3 to get the QSPI support. That is also going to require a bit of restructuring inside ArduPilot, because to gain the most benefit from having the QSPI flash support is going to require that we start marking up functions as being time critical, and that those functions should be, the code for those functions should be in RAM instead of flash, which reduces the worst case latency. The microcontroller will of course cache the code using its onboard cache. It's got a set associative cache it'll use for the code, but the worst case latency would be quite high if it has a cache fault and has to pull the cache out from across the QSPI. So particularly important for interrupt handlers. So we will definitely need to mark all of our interrupt handlers as being in RAM functions, but there'll be quite a few other time critical functions as well that we'll need to mark. And so we'll basically be giving up some of the RAM on these boards. Luckily, they've got quite a lot of RAM, and dedicating that RAM to being in RAM copies of the time critical functions. And so that'll just be a little markup on functions. So a little attribute that we put at the end of a function name to mark it, to place it into a section of the a flash segment in the ELF binary that gets copied to RAM at startup to make sure that it runs very, very fast. Any questions at all about the ChibiOS 20.3 shift before we move on?
Yeah, just on the Quad SPI, obviously that's quite a motivation from us to push on that as well.
Yeah, definitely.
Up towards that, hence Sid working on that.
Fantastic.
Yeah, look, one of the things that you're just talking about the time penalty, I'm very keen to see when we actually get there, because ST put a lot of effort into claiming there is no time penalty. So it'll be very interesting when we actually have the hardware to actually do some of those comparisons on those protocols.
Yeah, the cache control is going to be quite critical. Unfortunately, we've got fairly large data usage in ArduPilot. For example, the EKF uses 15, 20K per core, and it accesses that from the point of view of the microcontroller, an essentially random pattern. And we definitely need that cached. So I suspect that the cache algorithms are going to be struggling a bit with the prefetch from QSPI. I also suspect that the prediction, etc., that they've got in there is going to struggle, but it will be very interesting to start measuring it and seeing exactly how well it performs. But what we'll need to do is do some careful profiling. It may be worth actually getting some of the developer tools set up. There are ways of setting up STM32 so they can sort of stream real-time information, much more detailed information than you can get over ST-Link, out to an analyzer that can analyze the behavior of the microcontroller. And it might be worthwhile if Sid or one of our developers had access to those sort of tooling to be able to do some analysis of the performance and start adjusting, because profiling this stuff is quite challenging. But we just need to get it working first, and then we can do some course level profiling using our existing tools, and then start working out, what are the key functions we have to shift into RAM. We may even need to make it dynamic, where it actually depends on the configuration. So if people enable particular features, then we shift certain functions into RAM. Obviously, if they've enabled EK3 versus EK2, if they don't have EK2 running, you wouldn't want to have a whole lot of the EK2 code in RAM. You'd have that, just leave that in flash, leave it dormant. We might be able to just let the cache handle it, or we might need to do things in a more custom fashion. But that'll be something we'll find out in the coming months. And so at the moment, I'm just cheering on Andy and Sid from the sidelines as they do this very valuable work. But I have ordered one of those boards, that SP Racing board that's capable of doing this. Unfortunately, the post at the moment with the pandemic is not great, and it hasn't arrived yet.
Yeah,
any other questions on that?
Oh, the only other concern I've got with it, obviously, is as we start, moving things into RAM to make it easier to add more flash. Yes, we have now 4 times the RAM that we used to have.
Yep.
But I'd hate to see people getting too RAM happy, or any additional flash we had will soon be null and void by overuse of RAM. So please, everyone, be careful. Hardware's fun, but it has long cycles, and don't get too trigger happy on the RAM.
Yeah, that's right. That's right. We have we're at the moment the biggest RAM user actually on H7 boards. Even the default configuration is our buffering for the logging. We default that on H7 at the moment to 200K, just because we've got a lot of free memory, and so we might as well use it for buffering. And it means, you basically never lose a block to your SD card, even if you've got the cheapest, worst SD card around. But we can obviously pare that back and start using more of that for code once we start bringing in the QSPI work. All right, so moving on. So the next really big architectural change that I thought worth mentioning from the last year was the addition of the DAL, which is the data access layer abstraction. And this was basically the key enabling feature to allow us to do the new replay, high fidelity replay system. And Paul showed to very good effect in his talk earlier this morning. just how effective the replay is for doing analysis, being able to attune the EKF and also analyze any issues that you have with the Kalman filter. The DAL is an isolation layer between EK2, EK3 and the rest of ArduPilot. It means that the EKFs are only allowed to access sensor data, system state, etc., and timing information via the DAL. So it acts as like a choke point in the ArduPilot where the EKF is required to funnel all of its requests via the DAL. And the initial design of the DAL was put together by Peter Barker, and it did a fantastic job in getting the abstraction right. So thank you very much, Peter, for your work on the DAL and on the new replay. So by doing this, it means that we can log all of the interactions between the EKFs and the rest of the system, and log it very precisely. It means that the data structures that we log are in fact identical to the data structures that are used by the EKFs to access the rest of the sensor data, you know, all of our IMU data, baro data, timing data, etc. So it means effectively the EKF is reading from the log stream because it's actually the same log structure that is used when you have the accessor functions. And we guarantee this property by, we actually have continuous integration tasks. So every time you do a pull request, there's a CI task that links the EKFs to just the DAL and not to the rest of the system. And if it doesn't link, then that means that somebody's been naughty and they have gone and put in a function into the EKF that accesses a piece of data not going via these log data structures. And that would be a violation that would then potentially break the integrity of the replay system. For those who aren't familiar, the replay system is our way of rerunning the Kalman filter after a flight based on a log data. And it means we can change the code if we get an issue with the EKF, a state estimation error of some sort, and we want to try and apply a bug fix. We can actually develop the bug fix and then run that bug fix against the exact flight data from the flight in question where the problem showed up, and then compare the new behavior of the EKF versus the old behavior. It's an incredibly valuable tool, and we've had it for a number of years, but it basically it bit rotted for a while, and there was a couple of years there where the replay tool, its fidelity was poor enough that it wasn't really usable for its intended task. And with this new DAL system, it's now gives extremely high fidelity, and it's now very, very useful again. And so by locking it in this way through a CI, locking it in through this DAL abstraction, it's guaranteed that replay will remain as a useful tool into the future. We also, in the CI, we actually, we do a SITL flight test in CI, and then we run the flight test through replay, and we do a bitwise comparison of the resulting state estimation. And we check that, you know, to the bit, every single floating point number that is generated and integer that is generated by the EKFs is identical to the one in the original flight when we run it through replay, which is the basic hallmark of a good replay system. So that has locked things in. And so if you're wondering why there's, you know, when you're trawling through the EKF code, you see lots of references to this DAL function, that's why. And now we're not planning for the DAL to be used in the rest of the system because that would in some ways defeat the purpose of the isolation for replay. So DAL is an EKF only abstraction, but we have deliberately made the APIs for the DAL extremely similar to the APIs for accessing the rest of the sensor layers, which means that you should find it quite familiar. You basically replace, for example, you know, compass get field with DAL get field, and or DAL compass get field. And that gives you the same API, but via the DAL. So thank you again to Peter for his work on that, and that's going to be incredibly valuable going forward. So the next area that I wanted to focus on in this talk is what's been happening in AP file system. So AP file system is our abstraction layer for the file system. And it provides abstraction for the POSIX file system. So for example, the SD card, it allows you to access files on your SD card, but it's much, much more than that. And in last year's talk, for example, I introduced the param file system, which allows us to download parameters via the Mavlink FTP protocol. And essentially, that gave us a speed up of, much more than an order of magnitude in parameter download. And we've already had quite a few comments from users who are trying out the 4.1 branch, the latest builds of ArduPilot, that when they connect, they get much, much faster parameter download. And that's basically because Mission Planner, thanks to Michael Oborn's great work, has been extended to automatically use the FTP download of parameters when available. The same with MavProxy. So what I was going to talk about this year was we've expanded the AP file system a lot in the last year, and many developers and users may not be aware of the additional functionality. It's also that each time I give one of these system talks, I like to introduce a new feature. So over the last few days, I've developed a bunch of new features which I think might be of interest to a number of our users. And so I was just going to do a bit of a demo of these. So the key new features is I'm adding a @mission file system, which allows us to upload and download missions extremely quickly using Mavlink FTP. And it also gives us atomic mission upload. So when you upload 1,000 waypoints with the mission FTP Mavlink protocol, it's around 10 times faster, but it also means it applies those waypoints as a single unit once all the waypoints arrive on the vehicle, and rather than applying them piecemeal during the upload, which means that you don't end up with an inconsistent mission. So if you want to change a mission while the vehicle's flying, you can do so using a low bandwidth link much more effectively, but also not end up with half a mission at the other end. It will either apply the whole new mission or none of it, which is a really important property for, if you're doing large missions, particularly on a vehicle that is at the end of a slow telemetry link. It also handles fence and rally upload and download. So you can upload and download your fence points and your rally points. And just as a bit of extra, I've also added parameter upload using FTP. And that's much, much faster than uploading parameters using the existing protocols, roughly 10 times faster in my testing. That also has the nice property that it applies all the parameters in one go once they get onto the vehicle, which again ensures that you end up with consistent parameters. And it also gets over the property of the double download. People often, when they're setting up a new vehicle and loading 1,000 parameters from another vehicle, and you have to load once and then you re-download the parameters to fetch them again, because you've had a bunch of enable parameters. For example, QEnable, which enables the quad plane capabilities, or you're enabling a second battery monitor, and you then have to refetch the parameters, then re-upload again. And that's the dance that people are doing a lot at the moment. And they have to refresh and then re-upload again, and then acknowledge all the little OKs, etc., in the user interface. So that's fixed using this Mavlink parameter upload, and it uploads them all in one go, and it automatically handles the retries and the looping necessary within the flight controller so that it handles all the enable parameters correctly. So I'll just switch across to give a demonstration. So what I've got here, I've got a cube orange sitting here on my desk, and so there you go. I might as well give the full feeling. So there's my desk with there's a cube orange sitting in the middle of it, along with a whole bunch of other electronics. And this, of course, works with any of our flight controllers. And then over here, I've got a 3DR. An ancient 3DR radio, SIK radio, and so that radio is, out of my drawer from a long, long time ago that I've got connecting up to the vehicle. And so on the, I'll just share my screen again so you can see that again. All right, so so I'm connected into this vehicle here, and I'll just show you a few little features that we've now got. So first of all, you've probably already seen, so the parameter FTP, I can do that, and I can receive all of the parameters in the vehicle very, very fast. That's fetching the parameters. I've got both a USB link and this ancient slow SIK radio. If I set link 1, then I'll be using the SIK radio, and you can see here the parameter download that I'm doing here. You can see the little progress showing there and on downloading. So that was over that slow SIK radio downloaded the parameters in just a few seconds. And on the USB, it's basically instantaneous. So the new features is that what I'm going to do is I'm going to, I've got my map here, and I'm going to clear the mission. And then I'm going to do a waypoint FTP load, this mission that I've created. And so I'm going to do that. I'll do it on the USB one first to show you how fast it is over a USB link. Then I'll do it on the radio link. And what it's going to do is it's still loading that mission. It's loaded it all already. It only takes a fraction of a second over USB. And we can see we have a mission here, and this is taking advantage of the expanded mission space we've got in the in boards F7 and H7 boards. So we've now got up to about 1,300 waypoints we can have now. And so this is a 1104 waypoint mission created using the very cool little skywriting text mission from Mission Planner. Thank you very much for Michael Oborn for showing me how to do that. So we have ArduPilot DevConf 2021 as a mission, and we can load that very quickly. So what I'll do now is I'll just switch back to the slow SIK radio link, and I'm going to download that mission. So WP FTP, and to download that mission from the flight controller across the SIK radio. And you can see the little progress up here. So it's got about 200 now and coming up on 300. So it's making good progress, 400. And so this is the sort of link speed you might get with a slow SIK radio, you know, or like an RFD 900 running out to an aircraft in the field. And nearly there. There you go. We've now loaded 1104 waypoints, and it took, it takes around 20 seconds or so, a little bit less on these radios, which I'm quite pleased with. If I ran it with the old protocol, then we'd be waiting several minutes. It's about between a 10 and 20 times speed up over the old protocol. So it makes it much, much more practical. But more importantly is for many people is the fact that it's atomic. It means that when you end up with the whole mission as one lump, so you don't, if your aircraft is actually flying and you want to replace the mission with a new one, you can do so. It also does partial mission upload. Thanks to Tom for suggesting adding that to the protocol. So you could replace, for example, just the middle section using FTP, or just the end section, or just the beginning. There's flags in there for whether it should clear the mission when uploading. And that makes it really nice for doing partial uploads or shifts in pieces of the mission. So once this gets into our tooling, into the ground station, I think this is going to make dealing with large numbers of waypoints a lot nicer. I was also going to show you a parameter load. Actually, I might do that at the end. I'll wipe the parameters on the vehicle and load them from scratch as a demonstration at the end. But first of all, I want to show you what's been happening in the sys file system. So there's been a lot of extensions happening in the sys file system over the past 6 months or so, and work that's being done by Sid and Andy and myself in particular. And so there's a lot more files in here than there were last year. So we have, for example, you can look at a lot of system details. For example, if I go and get the sys memory.txt, and I'll just get it to minus in mav proxy means fetch it to standard output, which means it just displays it on the screen. right? So what that is doing, I'll just switch to the USB for faster. What that's showing is all the different memory regions. And there's actually 6 different memory regions, different types of RAM on the STM32H7 microcontroller on this particular board. And what it's showing us is the size of each memory region and how much of each memory region we're using. And we can see, for example, that we're using only about 10K or about 8K of our DMA-able memory. This type here tells us what type of memory it is. This particular one, if you know how to decode it, this means that this is the DMA-capable SRAM4 memory. And this one is the one that's used for the SDMMC, for the SD card. So you need to be a bit of a system developer to know how to decode these memory types. But it can be very useful when you're a developer looking at the performance and where your memory is going. So we can also download, so if I get something like DMA.txt, then this shows us the DMA contention. I'll just pop that at the top of the screen there. Might be easier to see. And I might raise my font size a little bit. So that should be a little bit easier to read for people particularly on the live stream. So this is showing us, how many DMA operations we've had on each DMA channel. And it's also showing us how much contention. Now, on this particular board, we're not, with this particular set of peripherals, we're not getting any contention at all. This is all 0% contention. If I had a different set of peripherals on here, I would start seeing DMA contention in this column. And very, very useful for analyzing performance issues. So if you do get problems with particularly UART to I2C and SPI contention causing performance bottlenecks, you can work out exactly what's going on here. And then we've got parameters that allow you to do things like disable DMA on a UART transmit or receive, for example, to prevent contention with another device like an IMU or an I2C compass or whatever. And so this type of analysis is incredibly useful when you're trying to do performance analysis on your board. Some other things in SIS, we can have a look at some CAN stats. So if I go and get the what's been happening on the CAN bus. So I've only got one CAN peripheral attached to this board. This second GPS is the nice high-tech Mosaic, their nice new Pro GPS. And so we should be able to see a few stats on that. And we can see exactly how many transmit requests. And we can see that we've lost one CAN packet. So we've had 1,580 transmit requests, of which one of them has been lost. And we've had, 1.5 million received packets since this booted. And you can see whether there's been any aborts or overflows or bus off errors, etc., which is really useful for seeing the quality and performance of your CAN bus. So if you're doing a lot of CAN work, you've got a lot of CAN peripherals, it's worth knowing how to look at the stats on each of your CAN buses and know what's happening with that. So you can also do a lot of analysis of things like the threads, how much memory you've got for each thread and the amount of stack space available. So this shows you all of the different threads. And as I'll describe later in the talk, we've now switched to a UART, a separate thread per UART model. And so you now actually have a separate thread for each of these UARTs, and you can see the amount of stack space being used. This is the free space and total space in this last column. And so we can see on the interrupt stack, we've got 1160 bytes, 3 out of 1500. So we've got plenty of spare room there. And you can see you want to check whether any of these are getting low. If this first column is getting very low, then it might be an indication that you're running things a bit close on stack space. And you can see the priority of each thread and where the memory is located. Another good one is the tasks. So that allows you to get some information on all the different tasks happening inside ArduPilot. You will find that when you first fetch the tasks, it'll give a failure. That's because we don't allocate the performance monitoring to generate this table until you fetch the task for the first time. So you have to fetch the task, then wait a few seconds, and then it starts populating that task set and then after that you can then fetch it. So I'd already fetched it earlier before I started the talk, which is why it gave it straight away. And we can see exactly what the performance is, the total CPU costs, and the minimum and maximum time in microseconds that each of these tasks is using. And so you can sort of nail things down a little bit as far as the performance costs, with brought down to some quite low level. You can sort of see, you know, the various update functions, logging functions, etc. And it'd be good, actually, I should probably work with Henry a bit more to put in some examples in the wiki and showing exactly what these numbers mean for when you want to do some performance analysis to see, you know, where your CPU is going. What else have we got here? We've got the UARTs, so you can bring up detailed information about your UARTs, and this shows you each of the UARTs you've got on the system, and you've got a little star here for the ones that are using DMA, and it shows you the sort of transmit and receive events, the receive number of blocks and that sort of thing. So it's again one that we should put up more information on, decoding this in the wiki. And then this persistent PAM, that's for when you've got temperature calibration on your IMUs, and it stores the persistent data inside Flash. It allows you to have a look at what that persistent data is. In fact, you can, in the factory, you can now embed a persistent set of parameters that will persist. They're persistent in the sense that even if you wipe your entire Flash by changing firmware, like from copter to plane to rover to blimp, it will still persist those parameters. So these are common parameters that are persisted even across a firmware type change. And that means that they can be placed into the firmware in the factory. Typically, you would put the temperature calibration data for factory temperature calibration in these persistent parameters, which means that when you ship the flight controller, that data is built into the flight controller across any future firmware, and it means that everyone will benefit from the factory temperature calibration. And I'm looking forward to that start being rolled out from the various ArduPilot vendors in the coming months, that capability, and start seeing some factory temperature calibration going on. All right, so that's probably enough information about the sys file system. And I was just going to show you the parameter upload. So what I'm going to do is I'm going to set the format version on this board to 0, which wipes my parameters when I next reboot. And so what I'm going to do now is reboot the flight controller, and that'll come back up again, this time with completely blank parameters. So it's now come up as just a default plane for this particular board, and you can see it's gone into failsafe because the default is throttle failsafe, and I don't have my transmitter turned on. And then I'm going to show you, so if I do param FTP to fetch down the current parameters, I'm going to set the link to the little SIK radio, that radio. All right, we're now connected over that SIK radio, and I'm going to do a param FTP load of my parameters. So this will now load all of the parameters of the vehicle via the parameter FTP protocol. So that's now uploading. You see the percentage going up there, and done. So it's loaded all of those parameters in just a couple of seconds, even across an SIK radio. So it's a very efficient way of downloading. If I now download all the parameters, it takes a little bit longer via the SIK link, but still very, very fast. It's half done. And there you go, all done. So if I now compare those parameters, you can see that the only differences are those ones you expect to be different, because we deliberately omit certain parameters like the airspeed, offset, mission total, number of resets and things from our parameter uploads. So that means that's demonstrated the way of restoring all the parameters onto a vehicle, including all of your enable parameters, and storing it very, very fast over a low-speed radio link. All right, any questions on that before I go back onto the rest of the slides? All right, so I'll move on. So what to have done that one and move on to the DMA changes. So there's been a lot of changes in the way we handle DMA in the last year. And a lot of this work was done by Andy Piper, and I really appreciate how Andy's dived into the lowest level of the HAL for ArduPilot, the ChibiOS HAL. It's done a fantastic job. So we used to use what's called binary semaphores for shared DMA. So ArduPilot has a slightly unusual feature in projects of this type, in that we allow for sharing of DMA streams between peripherals. So you could have a UART and an SPI bus both sharing the same DMA stream. And the reason we need that is because we have in ArduPilot a very, very rich set of sensors that a lot of people put on their vehicles. And they have more buses and more peripheral types than they have available DMA channels. Combined with the fact that there's each type of microcontroller that we support has different restrictions on which DMA streams can be used by which peripheral type. So, you know, for example, SPI1 might be on an F7 board, be able to be used by only 2 different DMA streams, you know, specifically numbered DMA streams. And I2C3 might be able to be used by a different 2 where there might be 1 in common. So there's this little matrix with overlap of DMA streams that are able to be used. And some time ago, when we did the HAL ChibiOS work, we introduced an automatic DMA resolver, originally written by Sid and then modified subsequently by both Andy and myself, that it tries to automatically allocate DMA streams to peripherals. And it can't do a perfect job because it doesn't know at runtime what peripherals a user actually cares about. So we can't really know whether the user is going to be using UART2 or not, or whether it's important. But we do our best, you know, to guess at the likely usage and allocate those DMA channels. So, but we allow this sharing, and by allowing sharing, we can use DMA for a lot more peripherals. And that means more CPU available for Paul to use in the EKF and for Leonard to use in his filters and flight control. And occasional others in the dev team get a look in and get a few % of the CPU if they're lucky for things like avoidance and that sort of thing. So now binary semaphores had the disadvantage that they can't do what's called priority inheritance, which means if a low priority thread is holding a binary semaphore on a DMA channel, and my apologies for for those of you who are not familiar with these sort of concepts, hopefully it'll become somewhat clear as I explain. So when a low priority thread is holding that binary semaphore, and a high priority thread comes along and wants that semaphore, it has to sit and wait until the semaphore is available. But that low priority thread may not actually be scheduled very quickly, which means that the high priority thread could be waiting for a much longer time than it really should. So what we want to use is what's called priority inheritance. And priority inheritance is a system in an RTOS where the lower priority thread that is holding up a high priority thread gets its priority automatically boosted to the priority of the highest priority thread that is waiting on the resource that it holds. All right, so basically that guarantees that it completes as fast as it should, according to the thread priorities we have. It means that our main thread doesn't sit around waiting for a low priority thread that is holding a mutex. Now, we have priority inheritance on mutexes in ChibiOS, but we can't do them on binary semaphores due to the way they're structured. And so we had to switch across to using mutexes, which required quite a bit of restructuring of the code, largely because mutexes have to be associated with a thread in order to do priority inheritance, whereas we were using binary semaphores in interrupt contexts in a number of places, particularly in things like DShot. And so thank you very much to Andy for doing that restructuring. And we are now switched across to using mutexes for our shared DMA, which is the first step along the way of the complete DMA restructuring, which is planned for ArduPilot. So the next stepping stone that I want to do in the coming months is to move us to dynamic shared DMA assignment. At the moment, as I mentioned earlier, we assign our DMA streams to peripherals at compile time, and we don't do an optimal job of it. In some cases, we do a very bad job of it. In some cases, we do a better job, but we basically can't do the perfect job because we don't know which peripherals are actually going to be used in practice. We do for things like IMUs. We know that the primary IMU is going to be used, but we particularly don't know it for things like the UARTs and for timers associated with things like DShot. And for the DMA streams that are associated with those peripherals, we can't make the decision accurately at compile time. So we'd like to use to a runtime optimization of our DMA stream assignment. And that restructuring really needed the new work with the mutex first to be done first to give us the new structure. And then I'm planning to start bringing that in after 4.1 is branched and start bringing in dynamic. And that should make for much better performance in some cases. At the moment, you need to go in by hand in some cases and disable DMA on particular UARTs to get the best performance. You shouldn't need to do that in the future. That should be completely automatic with the dynamic assignment of DMA channels to our peripherals. So look for that in an upcoming PR, and you'll be getting more performance out of your boards in future. We're also going to be moving to peripheral-aware DMA allocation. You may remember when I was doing that little demonstration before, and where we've got here the memory. So if I have a look at the different memory regions on this board, and you can see that there's these 6 different memory regions on the H7. And there's actually a complex matrix as to what peripherals are allowed to do DMA with what memory regions. And at the moment, what we're doing is we're cheating by using the SRAM4 memory region, which is equivalent to like O-type blood as far as donations. So the SRAM4 can be used for DMA for any peripheral except the SD card, but it's not optimal for just about anything. In fact, it's slow because to get to SRAM4 requires that the little memory requests get routed all across this complex bus, and which means our DMAs aren't nearly as fast as they should be. And so what we're planning to do is move across to a peripheral aware memory allocation scheme where we, when you allocate a piece of memory for a peripheral, you'll have to say what peripheral you want it for, and then it will automatically allocate the optimal memory for that peripheral based on what peripheral type it is. And that should make a huge difference. Well, we don't know how much of a difference it's going to make. We're hoping it will make a noticeable difference to our DMA performance, particularly for things like bidirectional DShot, which is very sensitive to timing of DMA operations. But we'll actually need to do some performance analysis to see how much of a difference it makes for other types of operations. But for latency sensitive operations like bidirectional DShot, we're expecting that it will make a significant difference. All right, any questions about DMA changes before I move on? Or have I sent you all to sleep? Nope, okay, moving on. So UART handling. So ArduPilot, back since 2016, we shifted to what we call the thread per bus approach to RTOS handling, where basically we have a separate RTOS real-time operating system thread for every bus in the system. And we did this for all I2C buses, all SPI buses, the ADC, and the analog in, and some of the other buses like SD card and things, but we didn't do it for the UARTs. And the reason we didn't do it is we were concerned about the amount of memory being used by the stacks for all of those UARTs, because quite a few boards have a lot of UARTs. So I think the one with the record, I think it might be 8, is the Maytech. I've got it on my desk here somewhere. There it is. Maytech H743. And so we've got an enormous number of UARTs on that board, which is great, really good for users to be able to have so many UARTs. But with a thread per UART, that's an awful lot of stack space. And so back in 2016, we made the decision that we would have a single thread for handling UARTs, and we would operate on each of them asynchronously. And so Andy Piper identified that that was a significant bottleneck, and in the performance analysis work that he was doing. And I completely agreed with him. And so we ended up switching just in the last few months to a thread per UART model. And what we found was that the reduced latency in dealing with UART requests meant that we were able to reduce the buffer sizes on the UARTs considerably. And it meant that even though we're now paying for a lot of stack space in our UARTs, so an extra 600 or 700 bytes of stack per UART, we save more than that in terms of the reduced buffer space we need per UART. So this change actually meant that we got our cake and can eat it too. We gained performance in our UARTs and we reduced the total memory footprint of ArduPilot, which was really nice to see. It was a very big win. And so this means that our UART responsiveness is now much higher. It means that with a dedicated thread that's sitting there waiting for data on that UART and waiting to pump more data out as the UART has space available, we're able to get considerably better throughput on all of our UARTs. And this is most starkly seen with, we changed the way we do the buffering on the USB, and we ended up with about 3 times the log download performance on H7 boards for log download over USB. But it's also considerably better over, high rate UARTs, and it's basically made us a lot higher performance overall. So, so many thanks to Andy for his work on that. And I hope everyone appreciates the additional speed up that they're getting and less contention. Any questions on our change in UART handling before I move on? All right, CAN changes. So there's been a lot of changes in CAN in the last year. And now Sid has led this work, though it's also been quite a bit of work from other people, Tom Pittenger and myself, among others. But Sid's really done the lion's share of this work. And in particular, he's done a completely new HAL CAN abstraction and a test suite that goes along with it, which is really great to see. So that new HAL CAN abstraction made it much cleaner for implementing new CAN protocols. And so it's now possible to add a new custom CAN protocol with really what amounts to about a page of code or less. It's just you can instantiate a tiny CAN, you can basically subclass a CAN driver class and then just implement the parser for your new type of CAN packet, which makes it absolutely trivial to add a new custom CAN protocol. Whereas previously it was a lot of very complex work to handle all of the CAN events and the registration, etc. We also support CAN bus ordering, so you can now, if you've got a board where CAN2, the STM32 CAN2 is logically your first CAN for your connector, you can make it the first one. You can have CAN2 and CAN3 instead of CAN1 and CAN2. And so we now support CAN3, whereas previously we only supported CAN1 and CAN2. On boards that have a third CAN bus like that, you can have, you can have CAN2 and CAN3, for example, on a G4 board, which I added that support for that because I had a G4 board that had CAN2 and CAN3 on it. And as you saw earlier, I showed you some of the @sys logging. We now have a lot of CAN diagnostics showing up in the sys file system, which is really useful for diagnosing what's happening. So basically, over the last year, we've seen a massive amount of CAN adoption, particularly UAV CAN adoption in the ArduPilot community. And it's really been pleasing to see. It was actually one of my major goals for the year that we would get wider adoption. And I've been delighted at the number of partner companies that have brought out CAN peripherals based around AP-perf. and there's been, you know, dozens of boards produced that are now out there in production use, which is really fantastic. Now, the next major step, as I mentioned earlier, and this is the question that Hamey asked, is about starting to support the higher data rate CAN. Because our H7 boards, as long as they've got the right transceiver on them, can do FD-CAN, which means they can do sort of 5 megabit or more, even 8 megabit, depending on the transceiver, instead of the 1 megabit. And just as importantly, they can do much larger packet sizes. So FD-CAN, you can do 64-byte packets, for example, instead of 8-byte packets. And so the overall overheads is much, much lower. It still uses 1 megabit framing, but the payload is run at the higher data rate. So it's the FD is flexible data rate CAN. And it means that your data portion of your packet can run at a higher rate, which means the overall bandwidth you have is much higher. Now, it's a little bit troublesome mixing your CAN 1 megabit and the higher data rate on the same bus. There are some strategies for doing that, but they're quite tricky. And it is things that we're looking at possible strategies. There's two different routes we've got to take advantage of FD-CAN going forward in ArduPilot. One is to adopt, so UAV CAN v0, the UAV CAN v0 standard, or v0.1 is often called, what it used to be called, you know, v0.9, and then it was like downgraded to 0.1, which was slightly odd. So it was designed for the 8-byte packets, right? So the standard is all around the 1 megabit 8-byte packets. And the UAV CAN v1, which is really just getting going at the moment, is designed to support the higher packet sizes. It can do both the 1 megabit or the 5 megabit, 8 megabit packets, and also the higher packet sizes. But it requires completely new packet definitions, protocol definitions, and it's a major disruption. So Sid and I are discussing two different approaches we can take to taking advantage of FD-CAN. One is to support UAV CAN v1, and I do think we want to support that optionally in the ArduPilot community. And the other is to do a v0.1 variant with supports fast data rates and larger packets, which would mean that that would be a easy upgrade for peripherals that are capable of doing FD-CAN. And I'm quite keen on doing that because it supports all of our existing packet types just faster. And the new CAN HAL layer that Sid has done would make this very easy, because the splitting into the framing of the packets is done in one place in the CAN layer, which means it would be very easy to just have an option to switch that. And what I'd really like to see is have a CAN option that says, you know, auto detect if all of the devices on the bus are capable of the higher speed, and if they all are, then broadcast a message from the flight controller to say everyone switch to the higher data rate if this option is enabled. And that would give us a really nice way of taking advantage of the high data rates. So we'd also like to support UAV CAN v1, and I'm expecting that we'll do that over the next year. But it's slightly frustrating, the shift to v1, because we're just starting to see lots of adoption of UAV CAN in the community, and it's rather tricky, the v1 switch, as far as handling the bootloaders and handling the different firmwares you'll have to load. On a lot of boards, I'd like to support dual stack, where it actually automatically determines whether it talks v0 or v1. And it may well do that by looking at what the DNA server, notice who the DNA server is, and then the DNA server, which is usually the flight controller, would make an announcement to say, you know, we would like to run v1. It is possible also, v1 has been designed to allow the mixing of v1 and v0 packets on the same bus, but I don't think that's been tested in practice by anyone. And so we'll have to just see how well that actually works in practice. So that's a sort of a bit in flux at the moment, and I'm sorry I'm being, so vague in exactly what's happening with the high data rate cans, and it's because we really aren't certain exactly how well all of this will really work in practice. But I'm expecting that over the next 6 months or so, you're going to see a lot of activity in this area. So stay tuned. The big advantage we do have is that because we've had high adoption of AP per if in the ArduPilot community, if we enable these new features in AP per if, then it means that everyone's going to be able to get these new features very quickly with just a recompile and just rebase on the latest version, the latest release of AP per if, and then you end up with the new features. So that means that these new features aren't going to be quite as disruptive as they would have been otherwise. All right, any questions about CAN at all before I move on? And how am I going for time here? I think I've been waffling along for quite a while already. All right, let's move on. So AP per if, I'll just do AP per if very briefly because Tom's got a dedicated talk to AP per if. I was originally expecting my talk to be after his, but we rearranged the schedule a little bit. So we've had really good adoption of AP per if throughout the vendor community, which is fantastic to see. And it's been great, the feedback we've got from vendors. We greatly appreciate it. For those who don't know what AP per if is, I suggest you look at my talk from last year or look it up on the ArduPilot site. Lots of new features in AP per if in the last year: ESC server output, including DShot, ESC telemetry, dual CAN support, MSP output, full AP notify, and battery monitor support. It's really been a fantastic increase in functionality in the last year. And Tom's going to give you all the lowdown detail on that in his talk tomorrow morning. All right, Lua update. We didn't have a dedicated Lua talk this year, but Lua is actually one of the big things that's that's really been enhanced in the last year. And so I thought it's worth mentioning. There's been a massive increase in the number of Lua API calls. So Lua is our embedded scripting language that allows the ArduPilot flight controller itself to run, to asynchronously run a script or multiple scripts. And those scripts can interact via a very rich API with the rest of ArduPilot. And really the sky's the limit in terms of what you can do with Lua scripts. There's some fantastic examples, and if you're not familiar with it, I'd highly recommend you go and have a look on our YouTube channel for a bunch of great videos demonstrating some amazing capabilities with Lua scripts. But there's been a number of really fundamental changes in our Lua scripting in the last year since the talk by Michael Dubois, which really laid out the basis of Lua last year in ArduPilot. A lot of projects have started adopting Lua script to add new features. We've more than doubled the number of API calls, where I've got several hundred API calls now available in Lua. We now have support for Lua scripts baked into ROMFS. And this is something that a lot of people don't realize. You can actually take your set of Lua scripts that you want for your vehicle, and you can incorporate them into your build process so that the firmware that you distribute to your users bakes into it a set of Lua scripts. So this is ideal for things like Lua scripts that do something like, wind failsafe, where they automatically look at the wind state and the battery state to work out the endurance to get home, and automatically switch to RTL while you've got enough battery to get home with the known headwind on the vehicle. And this links in with the wind estimation talk that Paul gave earlier today. And so multi-copters can now estimate wind, and you could combine that with a Lua script to automatically come home when you've still got enough battery to get home. Similarly, if you've got a tailwind, you can actually RTL a bit later and get a bit more time on station if you know that you've got a bit of wind assistance to get home. We've already got scripts like that for fixed wing in the Lua one, and you may want to bake those in. You might want to take a feature like that and build it into the firmware customized for your vehicle. And so you build a custom vehicle firmware for your particular type of vehicle. bake in the Lua script and you build that into the firmware so that it doesn't rely on the SD card. So when the user swaps out the SD card with a different one, they still run the same Lua scripts. And this is absolutely critical. If you want those Lua scripts to be flight critical functions, then you really need to do that. Some highlight other features that have come in the last year. We now have much more extensive mission control, and there's some great examples from Buzz in particular on how to create complex missions and modify missions on the fly using Lua scripts. Much richer access into our AHRS functions for IMU and attitude state estimation data. Lua script access into the proximity data for making decisions about proximity to objects and object avoidance. You can write I2C drivers in Lua now, so you can actually go and access the registers on an arbitrary I2C device and add support for sensors that ArduPilot doesn't have in the main firmware, which is great if you've got something like an I2C humidity sensor or radiation sensor or similar that you want to build in. You can write a Lua script to write that driver as a script, then bake it into ROMFS and get it to start reporting data down to the ground station or into the log. Analog input, PWM sources for pulse width sources and GPIOs, and that's just a small sample of some of the new APIs we've got. There are literally hundreds of new APIs that have gone in the last year. So really fantastic work that's been right across the dev team. We've got new APIs from a dozen or more members of the dev team, and it's been really great to see the blossoming of the Lua ecosystem within ArduPilot. So any questions about the Lua updates? All right, new IMUs, a lot of new IMUs supported. The ICM4, XXX, 4XXX, these are the variants. I'm really excited about those. And they're a major upgrade from InvenSense. And I'm looking forward to vendors starting to incorporate those ICM4 series IMUs in their products. They can, of course, use the HWDEF system. If they're thinking of it as a future upgrade, they might like to add it in as a automatically detected IMU now, so that if and when they do start including that new IMU on a future update, that it would then be automatically detected. These new IMUs offer a major upgrade in terms of lower drift, better cross-axis, less cross-axis coupling, and much faster sample rates, lower bus utilization, lots of nice advantages in these new InvenSense IMUs and much better APIs. So really nice to see that as an enhancement. We also support the new ADIS IMUs. I might have one of those here somewhere. There's one. So this is one of the ADIS IMUs. This was on an MRO board. And that big white lump there, like a sugar cube, that's an ADIS IMU, very high quality, quite expensive, but very high quality IMU. That's also in the CUAV X7. So there's a CUAV X7 board, and the reason why it's so tall here is to incorporate that much larger IMU. So there's these very high quality IMUs are now supported by ArduPilot. And the third type of IMU we've got, really big one in the last year, is external IMUs. So I've got a photo down here of a vector nav, and I've got one on my desk here somewhere if I could find it. So that's quite an expensive, that sells for, I don't know, $3,500 to $4,000 US, I think. And with a high quality IMU, plus it includes a full AHRS system, so state estimation, etc. And we fully support that. We can use that either as just an IMU, or we can use it as an IMU Barrow GPS, including GPS heading, or we can use it as a full state estimation, and we can actually have it in parallel with the onboard EKF2, EKF3, and run them in parallel. And then select, in flight, you can actually flick between the different state estimation systems. So you can run it as a ride along if you want to. That's a fairly major change at ArduPilot, and I'm expecting more external IMUs to support it in future, more serial connected IMUs. There's already a number that are candidates that are being looked at by various people to support more of these very high-end IMUs, and looking forward to somebody doing a fiber optic gyro as an external on ArduPilot. It should be quite easy to add one of those if you can afford to buy it. And of course, I'd be very happy to develop a driver on a fiber optic gyro if somebody wanted to send me one, a serial connected FOG.
Hey,
Any questions at all about that?
We had a question from YouTube.
Oh, yep.
Does AP-perif support Lua?
Actually, interestingly, so embedded Lua scripts inside AP-perif is coming. There is actually a branch that's been developed that has Lua scripts within AP-perif. The current releases of AP-perif and current master AP-perif does not run Lua scripts, but it is coming. Now, the people who have done that work, I don't know if they're happy for me to reveal who it is, but if anyone on the call is happy to put their hand up and say that they're the ones that have been doing it. Anyone?
Good. All good. Talk about
all good. Okay. Yes. Thanks, Philip. Yes. So I can reveal that Hex has been with Sid and Michael and have been doing that work to support AP-perif inside, sorry, Lua scripts inside AP-perif peripherals. And which means you can do, for example, you know, on the trivial end, you can do very fancy LEDs inside a peripheral. But of course, you can do a lot more serious work as well. And so that's a fantastic addition. I'm looking forward to getting that in. But that is still being developed, and I'm expecting that in the coming months, you will see Lua scripts inside AP-perif, particularly baked into ROM-FS inside AP-perif would be the typical way of doing it rather than on an SD card.
Cool. We also have one other question that's just come through. AP-perif IMU.
AP-perif IMU is coming.
Like the VectorNav, but
indeed. So AP-perif IMU is coming soon because I have a board with an AP-perif based board with an IMU that is actually in the post to me right now. And but I could also, of course, prototype it on any of the existing flight controllers that support a build as an AP-perif, like any of the MRO PixRacer Pro, the Cube Orange. Any of those can be done as an AP-perif. So yes, IMUs in peripherals is coming, but this will become important as far as bandwidth with FD-CAN, because an IMU, depending on how you're using it, if you're using it for sensing vibration in a motor, for example, say you've got this built into an AP-perif ESC, which is also coming, by the way, ESCs, AP-perif ESCs are coming. So if you've got it built into an ESC, then you might like to use the IMU to detect high vibration for pre-fail detection or logging and post-flight analysis on your ESCs. And if you're doing that, you're going to need very low rate. You might have like the RMS vibration coming back at sort of 5 Hertz, 10 Hertz or less. But if you're using it to actually as a input to your state estimation or attitude control, then that means you need that IMU data at a much higher rate, and that means bandwidth. And this is where the high rate FD-CAN support is going to be so important. And that's where the work that Sid is looking at soon for high rate FD-CAN support, both on B0 and B1, is going to be the enabling technology to enable the high rate IMUs on CAN bus. So any more questions on the IMUs before we move on?
Yeah, Olivia's just posted another one that came in through YouTube. They've asked, with regards to the external IMU, does this open the door for having multiple controllers linked rather than just the external one?
Yes, and potentially. At the moment, we don't have a way. We do have a piece of code that can output the VectorNav protocol, but we only did that in our simulator. We've got basically a VectorNav BN300 simulator. Now, we haven't yet done the work to move that into our code, a bit like we've done the NMEA output. So those of you, I mean, if you're familiar, that you can just set a serial 5 protocol equals and then the right number for NMEA, and any UART in ArduPilot can become a NMEA source, right? Which means it essentially becomes like a GPS for another system. It would be really nice to be able to set a, serial 5 protocol equals a external AHRS protocol, and then you could have that as an input to another system. the main question is the handling of the latency of that, but it is doable. It should be doable via both CAN bus and via a serial UART. And so yes, I expect we will support this in future, but right now we don't have the generation functions for that in ArduPilot Master. That's an upcoming feature. If it is an important feature for you and you'd like to see it pushed up the priority list, then please open an issue, or if you're a partner or a vendor and you want to help fund that work, then feel free to get in touch with the developer to push that along a bit faster. But that is going to be coming because that's on my roadmap of things to do in the coming months. Any more questions there?
Nothing from YouTube at this point.
All right, so I'll move on.
Last one though, Tridge, it was more about redundancy or distributed flight control, more so than...
Yeah, and there are some vendors who are actually flying in production distributed flight control. There's some with multi-rotors, for example, and they've built up custom systems utilizing the existing capabilities in ArduPilot, then extending it. And critical components of that is things like the standby mode that Leonard added for Copter, which is really important when you're doing, a redundancy between flight controllers. It would be really good if we gave a bit of a how-to in our wiki on how to build a redundant flight controller system with ArduPilot. It is doable now because a number of vendors have done it and are flying it in production, but it is a bit of a black art in terms of how to get all of the pieces in place. But these types of output protocols and CAN bus protocols are an important part of this. Yes, hopefully over the next year, we'll start developing the key pieces to make that easier to do and start to document how to do that. And we'll get more people running redundant flight controller setups. All right, so diagnostics and error handling. So we are coming near to the end of the talk for those of you getting systems development fatigue. There's been a lot of improvements in diagnostics and error handling in the last year, a huge expansion in the AP internal error system, particularly from Peter Barker and also Michael Dubois and others. So we now have source line numbers when we generate an error. So tell us exactly, what line of code generated the error. And we have a much wider range of errors reported, which is really useful for log analysis. We've got a huge number of improvements in the area of detecting and preventing stack overflows, which is really nice because we did for a while there, we were a bit low on stack and we got a couple of flight controllers hitting stack overflows. And so that's been fixed up and we've got much better diagnostics on that now. We've got a new memory corruption detector, which is a compile time option, but very useful if you are getting any memory corruption, which is always a possibility in a C++ project. So we've got optional guard regions on memory allocations, which is very useful for detecting memory corruption. If you want to use that, then you should probably talk to me about how to enable that and use that. We also have a new storage backup restore system. This was part of there was an issue with some flight controllers, in fact, quite a few flight controllers with corruption of storage. And so we now have an automatic backup system for our storage if you're on FRAM. If you're on FRAM and you're on F7 and H7, we do it. And then we automatically restore the corrupted parameters. We do flag an internal error at this stage, but it means that you don't lose your parameters. And that's been one of the more annoying issues we've had over the last year. It was very, very difficult to track down. And I'd like to thank all of the vendors who participated in the diagnosing and assistance with that, particularly HEX and CUAV. Both were heavily involved in diagnosing and dealing with ways of dealing with that particular issue. All right, so final slide. So there's been a lot of changes and we're now ready for the 4.1 release, and the PR for Rover 4.1 was opened yesterday, I believe, by Randy. We're expecting the first beta releases of 4.1 for Copter in the next week or two, and then probably Plane shortly after that. quite long beta period we're expecting, because there's been, as you've seen from this talk, a lot of system level changes, and there's been a lot of changes in other areas of the code. So we really need people to jump on these beta releases and test them. So when the betas come out, please get testing and, more importantly, reporting both positive and negative experiences with the betas, including logs. Please fly with replay logging and log disarmed if you can for better EKF analysis. So really, everyone, hope you enjoy the 4.1 release. It's been a long haul, but really worthwhile. And thanks to everyone that's done the testing on the 4.1 alpha, the latest releases over the last few months. And happy flying to everyone. Enjoy the ArduPilot experience. So any final questions before we wrap up? All right. So, well, if there aren't any more questions, then I think we've probably had enough questions with this, and we've gone on rather long, the talk. So what we'll do is I think we'll maybe take a couple of minute break now, and a sort of a toilet break and a coffee break. So come back in a couple, let's say 5 minutes. We can have general chatter between people if you don't need a toilet break, and otherwise come back in 5 minutes time. And we'll actually then be on schedule actually for the next talk. So, so see you all in a few minutes time, and we will, our next talk that we have, I'm just looking up what our next schedule is.
Yeah, it's me, I think.
Third talk is Randy McKay with the GPS, non-GPS navigation transitions. So we'll start at the top of the hour, I think. We'll start on that talk. And meanwhile, developers can chat among themselves. Thank you very much.